Okay. Good evening, sir. This is Mushrif speaking from YCCE Nagpur. Hello, sir.
Hello, sir, could you hear us?
Are you able to hear me?
Yes, now we can.
Yes, yes. Good evening.
Yeah, I can hear you.
Okay.
Can you hear me?
Yes, sir, yes.
Okay, good. Yeah, so good evening, good evening, good evening. So I am ready
Good evening,
when you
sir.
are ready to start.
Yes, sir, we will wait for a minute again to join another participants and we will
Sure,
start
sure.
within a minute.
So how many participants are there in the course? How many participants are there in the course?
Yeah. Hello, sir. 50 participants, 49 to be precise,
Okay,
and few students are also there.
okay, okay, okay.
Yeah.
Mushrif, sir, could we start? Others would join
Yeah.
subsequently.
Let us start.
Okay, Keote madam, over to you.
Okay, ma'am. Thank you. Good evening, one and all. I, Dr. Minal Kevte, ATAL FDP committee member, presents before you this first session of Day 4 in Week 1 of ATAL FDP RSAML 2023, organized by Department of Electronics and Telecommunication Engineering, YCCE Nagpur. Today, we have with us a learned expert from IIT Bombay working in the area of remote sensing, Dr. B.K. Mohan sir, as our speaker. Dr. B.K. Mohan sir received his PhD degree in electrical engineering from IIT Bombay in 1991, specializing in the area of digital image processing and analysis. He is currently a professor in the Center of Studies in Resources Engineering, IIT Bombay, and was head of center during 2014 to 2017 and an institute chair professor during 2016 to 2019. Professor Mohan's research interests include machine learning algorithms, segmentation and classification of high resolution satellite images, geospatial technologies, educational content design and development for GIS and image processing. He has 150 publications in journal, book chapters, and conference proceedings, and 30 plus sponsored projects, and 15 plus consultancy. He supervised over 60 students for MTech and PhD thesis. He recognized for his work by a way of holding associate editorship and reviewer in journals and BOS members in universities. He organized several training programs for in-service members of the academic community. Professor Mohan is the recipient of IIT's M.N. Saha Memorial Award for Best Application Oriented Paper published in IIT Journal of Research September 2000, and Indian Society of Remote Sensing National Geospatial Award for Excellence in 2012. Now I request Dr. B.K. Mohan sir to proceed for the session and light up all the listeners with your expertise.
Over to you, Mohan sir.
Yeah. So is my screen visible?
Yes.
So at the outset, thank you very much for inviting me for this program. And sorry for the inconvenience due to my request at a very late stage for rescheduling this talk from Monday to Thursday, that is today. And thank you for accommodating this request. I work in an academic unit of IIT Bombay. We have MTech and PhD programs in the area of geoinformatics, which is a multidisciplinary area with contributions from almost all areas of science and engineering. My colleagues come from various disciplines, and we admit students also from various disciplines at their BTech and MTech stage. So we have students with the masters in agriculture, earth sciences, civil engineering, electronics and communications, electrical engineering, computer science, mathematics, physics, and even architecture. So these are broad set of disciplines in which we admit students. Similarly, colleagues also, we have professors. I'm from electrical engineering at my PhD level. We have physicists, we have earth scientists, civil engineers, computer scientists, etc. So this field is such that it can draw upon the expertise of people from varied disciplines. And we use machine learning algorithms as a set of tools for analyzing data about our Earth surface acquired by sensors and cameras mounted either at a few meters altitude like UAVs, or a few kilometers like aircraft, and a few hundreds of kilometers, that is satellites. Okay, my lecture is implicitly assuming that the data is coming from space-borne sensors. Okay, even though some of the methods can very well apply to aircraft and drone images as well. Now, given that the machine learning applications are very closely linked to the data, for which they are built, so you have some algorithms that are well suited for medical images, some for biometric images, some for natural outdoor scenes, and some for Earth observation purposes by sensors operating from a distance okay, without physical contact with the target. Okay, so in order that we get a proper perspective about what we are discussing today, I would spend a little time explaining the principles of the underlying data. Uh, and of course, this would have been much more appropriate in the first day, but assuming that at least some of you are new to this field of remote sensing and its applications, maybe a slight repetition uh, would reinforce your understanding of the domain from which the images are collected. So I suppose by now you'd have got the basic definition, working definition, let's say, of remote sensing. It's the art and science of making measurements and observations. So it's an art because sometimes it's not easy to get the right kind of sensors, or even if you don't have the right kind of sensor, still working with that for your application. And the science, the physics and the chemistry, the chemistry of the target and the physics of propagation of radiation uh, between, say, a natural source like the sun, how the solar radiation passes through the atmosphere, incident on the Earth's surface, gets absorbed, reflected, and then how the reflected energy passes through the atmosphere again, what uh, interaction processes take place in this two-way propagation, and finally what is received at the sensor. So there is a lot of underlying physics and of course electronics involved. So the key thing is that there is no physical contact between the sensor and the target. Of course, we have again a whole set of instruments and applications where the data is collected in the field. We call it in situ data collection or in situ sensing. Usually, the in situ sensing or in situ data collection is used to validate the inferences made uh, from the analysis of remotely sensed data. Okay, so at selected locations on the ground, that some data is collected usually for validating the observations made of the analysis of remotely sensed data. So today you have a very wide range of these imaging sensors. Some are commercial, some are government launched, so they are given away at a very low cost or given away free. So you have imaging sensors from space, from aircraft. So for example, the hyperspectral imaging systems, we have both built by NASA, called the Advanced Visible Infrared Imaging Spectrometer, or the AVIRIS, and its next version called AVIRIS New Generation, or NG. At several locations in India, AVIRIS NG sensor-based data was collected, and now this data is available for free download from ISRO and NASA Jet Propulsion Lab servers. Okay, you can do a Google search for the sources. We also have non-imaging type of sensors where set at a given location, data is collected, like altimeter, which is generally used for wave heights, right? Usually in oceanography applications, the wave heights are measured using altimeters. Scatterometers at selected locations, the backscatter, usually in the microwave part of the electromagnetic spectrum. And then you have laser based sensing or LiDAR, light detection and ranging. So, LiDAR data can be interpolated and made to look like images, but it is essentially collection of measurements at point locations. So you build what are called point clouds from LiDAR. All of us are familiar with this electromagnetic spectrum at a very narrow range of wavelength bands. We use for data collection for Earth observation, the visible region. Let me use the laser pointer. So we have in the visible region and then beyond the near infrared, mid thermal infrared, microwave. So in some of these wavelength bands, data is collected for Earth observation and applications. Okay, on the left side, this portion is used for studying other planets, stars, and far distant galaxies. And on this side, we use them for medical applications, for ship-to-shore communications, and some of the others. Essentially, if we limit ourselves to remote sensing in a passive mode, that is, we don't have any source of energy packed with the sensor, but if we use the natural source of electromagnetic radiation, that is sun, so the solar radiation incident on the Earth's surface gets reflected, and the reflectance itself is a function of the wavelength of observation. So in some wavelengths there is high amount of reflectance, in some wavelengths there is high amount of absorption by different materials on the ground. So you have water has one kind of behavior, green vegetation has another kind of behavior, dry soil yet another kind. So if you have the sensors operating in appropriate set of wavelength bands, you'll be able to collect the data and with which you should be able to discriminate between different kinds of target objects on the ground. Okay. So again, an assumption which is not very easy to fulfill is that each object on the Earth's surface has a unique reflectance pattern as a function of wavelength. So this unique pattern requires that the observations are made in a large number of wavelength bands. You must have seen these patterns in your introductory lectures. So the x-axis shows the wavelength, the y-axis shows the amount of reflectance in percentage. And if you see, the green vegetation has a very uneven kind of, slightly, very low reflectance or high amount of absorption. At the green wavelength, slightly more. And then when it comes to red, there is more absorption. And immediately after red, when you come to near infrared, just after red, you have a very high amount of reflectance. And then you go further into other wavelengths due to water vapor and due to the cell structure, etc. You have low and high reflectance, etc. So depending on how many wavelengths in which you are observing this, you can establish this kind of a pattern, which is very unique to healthy green vegetation. If you see the blue, this is for water. So what you can see here is that generally water absorbs most of the incident radiation, but in the infrared region, there is near total absorption. So if your images include what is acquired in the infrared band, you'll be able to get a very sharp land-water boundary. Okay, this is for dry soil. So you have progressively increasing amount of reflectance as a function of wavelength. Okay, so you can build up. These are built using either laboratory studies or field studies, and then they are used as a guideline for analyzing the space-bound data. Now, we know that with appropriate set of wavelength bands in which if the sensors are operating, you'll be able to discriminate between different kinds of objects on the Earth. At the same time, you should also ensure that whatever is getting reflected from the ground, it should reach the sensors which are up in space hundreds of kilometers above the Earth. So which are those wavelength bands where the atmosphere also cooperates? Okay, for which the atmospheric physicists through many studies had given us a spectrum, transmission spectrum of the atmosphere. So you can see that in selected wavelengths, you have a high amount of transmission through the atmosphere. So the attenuation is less, and so the radiation can reach the sensors, okay, which are operating much above the atmosphere. You have certain wavelength regions where there is absorption, very little transmission. So you have to choose the sensors. If you want to use them for Earth observation, you should choose those wavelength bands where you have high transmission. If you want to study the atmosphere, then you should choose those wavelength bands where the absorption is there. Okay. So if you invert this, you get absorption windows. Window means a range of wavelength band, a range of wavelengths. Okay. So these are very, very handy for designing the sensors. So they should have distinct response for different materials on the earth, like soil, water, vegetation, and then snow, shadows, clouds, different things. Okay, so the sensor should be capable of collecting relevant data, and it should be possible to distinguish between different objects. Okay, the target material properties and the transmission attenuation properties of the medium, they together determine the specifications of the sensor. Okay. Now today you have across all the continents put together, a very large number of Earth observation satellites owned either by industries or by governments, which can provide you the data. So you should know for your application what is the right uh, specifications, right? So what are the specifications? One is, what is the smallest area on the ground that can be uniquely captured by the remote sensing system? Okay, that relates to the spatial resolution, the ability of the sensor to resolve between closely spaced objects on the ground. Okay, so it's also related to the instantaneous field of view of the sensor element. So if you are particularly working in urban areas, so you have large buildings to very small hutments, big cluster of trees to individual trees, huge highways to very narrow passages. So you have different things at different physical sizes and with different kinds of geometries as well. So the spatial resolution plays an important role when you want to study such things. Now, another specification is the number of spectral channels, wavelength channels in which the data is collected. Now, when you have similar kinds of target features, the spatial resolution alone may not help. Like clear water and polluted water, different kinds of road surfaces, uh, you know, uh, similar looking trees, but which are actually different, which belong to different species, or healthy versus some disease affected vegetation. So if you have many wavelength bands in which you're collecting the data, the differences in the reflectance as a function of wavelength will reveal the differences. Okay, the spatial resolution may not be of that much help. Okay, that is the spectral resolution. Suppose you are a forester or an agriculture specialist, you would want uh, a very good spectral resolution to monitor the forest cover, the croplands, etc. Radiometric resolution, whatever energy that is reflected from the ground, when it reaches the sensor, it's converted from light form to electrical form, electrical signal, and then it is digitized and quantized. So how many bits are allocated to this quantized signal? That is the radiometric resolution. So in any single wavelength band, if you have more bits, it means that any tiny difference also in the amount of reflectance can be captured when you have high amount of radiometric resolution. Temporal resolution means the same area on the ground, how often can it be captured? Once upon a time, there were very few satellites, so it was an issue. But today, when you have so many satellites, practically every day you can get these images. So this is not a critical specification today, but it was, say, 15, 20 years ago. So a few examples, you must have already seen some in the other lectures. 2 feet, so each pixel covers 2 feet by 2 feet on the ground. About 6 meters by 6 meters on the ground. Mumbai airport, runways and the holding areas. This is about 23 meters by 23. That is, each pixel in the image covers this much area, 23.25 meters by 23.25 meters. Okay, so what you can see, if we go back, the images of this kind of, this is spatial resolution, right? These numbers relate to the spatial resolution. So you can look at the geometry of the buildings. You can see the layout, the topological relation, like you have a set of buildings in the left right direction and some in the north south direction, so they are mutually perpendicular. Similarly, you have some more buildings like this. You have water bodies which do not have a regular shape, and then you have a long ribbon like structure which denotes the road. You have vehicles on the road. You have a hilly surface, the hill shadow here, buildings and building shadows, a ground with a cricket pitch. In the north of the image, what you see here is all the weeds and water hyacinth in the Powai Lake. This is all outside and further ahead of IIT campus. Okay, all of it is basically Powai and nearby areas. Okay, so you can think of images like this as a collection of small or medium size or large objects. Okay, so these are like large objects, the water bodies, and then you have collections of these objects, very small objects that are the vehicles on the road, very narrow passages here, fairly wide roads. Okay, so the amount of information, it's collection of its objects with their geometries, and then you have spectral information in terms of the as a function of this way. This is called a false color composite made up of near infrared, red and green channel data. So you can see the texture created by collection of trees. This is a grassland, so you have very uniform pinkish shade, and here you have all healthy green water has in the weeds which have a reddish appearance. So here the darkish shades denote dark green leaves, trees with very dark green leaves. So this is, I mean, a trained interpreter can make use of, readily analyze and explain what's in the image as such. Okay, at this resolution, when you see the image, you can see some kind of a textured pattern, like you can see checks, buildings with roads in between. Okay, you cannot see the individual buildings with the kind of detail that you saw in the high resolution image. But-
Sir, sorry
Yeah.
to interrupt. I have one question over here.
Yeah,
These are true color images or
false
composite
color.
color?
These
False
are
color
FCC,
images. FCC
false
images.
color.
Okay, okay.
Yeah.
That's why the red color and others are there, right?
Red color denotes vegetation.
Yeah, yeah. Thank you.
Vegetation or grass. Yeah. Okay, so why I'm explaining this is when you design your machine learning algorithms or image analysis algorithms, you should look at what are the characteristics of the images and what kind of analysis methods are best suited for this for this, not for this. Okay. So here the spectral as well as the textural properties can be exploited for analyzing images of this resolution. Here, images like this are fairly amenable to object-oriented image processing or image analysis. So you can break up the image into collections of homogeneous regions and then relate those regions to actual objects on the ground. Okay. Whereas here, at the very relatively coarse resolution, it is only the spectral properties. So you cannot make out any building or anything. They are all smoothed out due to very coarse resolution. Okay, only which are very large. For example, this is a large, very highway that you can see. This is the creek that separates Greater Mumbai from Thana. These are the lakes: Bihar Lake, Ovai Lake. IIT's campus is all located here. I'm sitting in some pixel in this. This is the tip of the Mumbai airport runways. You have some clouds and cloud shadows. This is all the Sanjay Gandhi National Park, the north of Mumbai. These are all mangroves. This image is slightly old actually. So today we lost some of the mangrove cover. With time, some of them might have died, or some of the land is converted for other purposes. Okay. So given the application, what is coarse resolution for one application can be very high resolution for a different application. Okay. So this example I have given, 250 meters by 250 meters may be high resolution for ocean studies, because oceans run into lakhs or millions of square kilometers. And for mapping buildings and roads, this is extremely coarse resolution, low resolution. And this is medium for urban applications. Okay, so depending on if you want to just plan a new city area, a new township, this may be appropriate, because all you need to do is mark out which will be the residential areas, which will be the commercial areas, industrial areas, etc. So this may be enough. But if you want to analyze an existing city or a town, and you want to look at different kinds of settlements, transportation network, sources of water, the urban vegetation cover, etc., you may want a much better resolution than this. Okay, and you may also want hyperspectral data if you want to distinguish between road surfaces, between the tree species, between polluted and better quality water, etc. Okay. So space-bound hyperspectral sensors are not easy to get today. We don't have any in the world of good resolution, but there are cameras available, hyperspectral cameras available that can be mounted on drones, and you can get these images for any area of your choice with pretty good spectral and spatial resolution. So high spectral resolution, what you see is these circles. These are all like adjacent wavelength bands. Each one is as narrow as a few nano or 10 nanometers or thereabouts. So you get near continuous reflectance spectrum. Okay, this is for, you must already know now by now that it is for have green vegetation. So with hyperspectral images, you have so when you want to apply your machine learning image processing algorithms, the challenge here is the dimensionality of the data. So each pixel is associated with hundreds of features. Okay. So what kind of algorithms you use, uh, as we go along, we'll try to address some of these things. But you have issues like, uh, you know, do you have sufficient uh, labeled pixels for training your classifiers? Okay. Or do you have this curse of dimensionality? How do you cope with it? So there are a lot of issues. So you have some images where there are large number of pixels, but the number of wavelengths in which the data collected may be just 3, 4, 7, or 10. But here with hyperspectral case, you have the problem of very high dimensional data. The image size may not be very big, but the number of wavelengths, okay, or the feature dimension of this data is very high. Okay, I put down a few sources for you where you get a lot of information about remote sensing, some free books, reading materials, etc. The last one, these are all very useful case studies, remote sensing applications, essentially. Okay, and you have some tutorials. Okay, so how do we process these images? Image acquisition, then pre-processing, improving the contrast, suppressing the noise, then break it down into segments or perform classification, feature selection, segmentation, feature selection, and finally classification. So these are the general steps. Sometimes after pre-processing, you may directly come here. You don't do any feature selection, but in some cases, you may come directly from pre-processing to feature selection. And with very high spatial resolution data, you would come this way. With high spectral dimension or a very large number of spectral bands, pre-processing, you come here. With coarse spatial resolution and very few bands, you can directly come from pre-processing to classification. Okay. So depending on the data, you go through all the blocks or you bypass some of them. Okay. Let us look at some simple classifiers for analyzing this kind of images. So when I say program classifiers, it means that I have the formula worked out. So given the data, I can tell you the class. Okay. So there is a very clearly defined way to relate the input data to the target class. So when I say target class, what I'm actually referring to? The satellite image comprises millions of pixels. Okay, that is raw data for an application. What is of interest is how many of these pixels belong to water, how many belong to vegetation, how many belong to built up areas, how many belong to, say, soil, desert, coastal regions, okay, snow covered areas. So, like that, we need a mapping from the numerical data associated with the pixels to symbolic data where each pixel is given a name or a symbol. Okay, so some pixels may be labeled water, some pixels may be labeled vegetation of type 1, some may be labeled vegetation of type 2, like cropland and forest land. Okay, similarly, sea and inland lakes, like in Mumbai. So the labels will help us count how many pixels are there under each category, and we know how much area is occupied by each pixel, so we can find out the total area of a particular land use feature. Okay, so how much is the forest cover north of Mumbai? If somebody asks a question, you can answer it. How much area is there in the mangroves? Uh, you know, or what is the surface area of the lakes? What is the length of coastline? You can answer many such questions. Okay. If you complete the classification of the image and label each pixel with some semantically meaningful label. So the underlying process is that a classifier has to learn the relationship between the input data and the target classes or the knowledge. Okay. And then, so how does the learning happen? The learning happens when samples are supplied, okay, saying that, okay, look at these few pixels, these few hundred pixels, they represent water. Another few hundred pixels, they represent, say, built up areas. Another few hundred pixels, vegetation. So, like that, if samples are provided, by analyzing those samples, the classifier can learn the relation between the input data and the target classes. So there are three things that we are looking at right now. One is the labeled training samples, that we call them training samples because the classifier trains itself to relate the input data to the target classes. And at each sample, what do you have? You have a set of what are called features in machine learning terminology. When I say feature, it means, in, say, for a medical application, when you go to a doctor, for the doctor, the features are the blood pressure, temperature, sugar level, other cholesterol levels, maybe the test done for thyroid functioning, liver functioning, kidney functioning, and so on. So those are the input features for a doctor. Based on that, the patient is, say, diagnosed or classified as having disease X or of normal health. Now, with the help of a few labeled samples, when the classifier learns, now will it be able to, on its own, analyze or classify new samples which were not shown before? It's like a student having to answer questions in an exam where the questions are different from what are solved in the class. Okay, the solved examples in the class are like the training samples. The test samples are like the questions given in the exam. So the generalization or ability to uh, properly classify the test samples, okay, uh, establishes that the classifier is ready for practical use or operational deployment. Okay, sometimes a classifier learns well but does not generalize well. This can happen if the classifier is given insufficient number of labeled samples. Okay, so as I said, we have training samples, that is sample data elements with their corresponding labels. Features are attributes or descriptors. Okay, and so they define the dimensionality of the problem space for the mathematical and machine learning purposes. So we are talking essentially of what's called supervised classification, because the supply of labeled samples in a sense supervises the performance of the classifier. Okay, so it is guided in the process of relating the source domain to the uh, knowledge, that is the target classes which the measurements actually relate to. So when you say we are characterizing the classes, or we want to classify the data, okay, so essentially what we have is, from the training samples that is given the class, we have a distribution of the data values. Okay, this we can compute given the training samples class wise, and this is what we need to estimate for every test element, okay, or every data element, new data element, that is given the features. Okay, since they are multidimensional, we call them feature vectors. Given a feature vector, what's the probability of each class? So you'll be able to assign this data vector to that class for which this probability is highest. Okay, so this needs to be computed after the classifier trains to relate X with the classes. So typically, what does the classifier learn? Okay, so it has to learn the characteristics of different thematic classes. So for each class, what is the mean reflectance, or what are the average sensor measured values, okay, in different wavelengths? What are the extreme values? Okay, so things like that, they are learned by analyzing the training samples. So this process of supplying samples is governed by the statistical theory of sampling. Okay, so it is a very well established discipline from the field of statistics. So typically what are learned? Mean vector, that is, if you are given a few pixels, you can find the mean of those. So that gives you the mean vector. And since you have multiple variables, you can not only find variance of each variable, but also covariance, how one varies with the other. Okay, and minimum and extreme values within each wavelength band for each class. Okay, so then this needs to be computed. Okay. Oh, sorry, actually this should be probably x given ci. Probability of x given ci, not ci given x. That is, what's the distribution of the data values in each class. So practically, how do you select the samples to display the image? You should have some familiarity with the area. So you can mark these sample areas for each class, and with which you will be able to then build all these things, compute all these things, and go ahead with the classification. Okay. So one of the simplest classifiers, before we go to more complex ones, I'm introducing the simple classifiers for those who are not familiar with this field. So suppose your training samples are distributed in the feature space. Suppose you have a 2D feature space, feature 1 and feature 2. These are samples of class 3, class 2, and class 1. And these are the averages or means. So suppose you have given a test sample whose values are here. So if you compute the distance from the mean, class 2's mean is closest. So this is assigned to class 2. This is the principle of minimum distance to mean classifier. So what you are initially given, you are told that there are 3 classes. For each class, you are given the samples. From the samples, you compute the mean. And now when you are given a test sample, find the Euclidean distance in the feature space, not physically on the ground, but in the feature space. What's the distance to each mean? And assign this to the class whose mean is the closest. So this is a fairly simple technique. So we're assuming that around the mean, all the samples are distributed in a hyperspherical region. Okay, so equidistance from the center in any direction, the sample will belong to that class. Okay, just put down a few steps for you. You can look them up later. I'll share the slides. So another example is, suppose from the samples, okay, here we have a 3-dimensional space. Let's say class number 1. So this is feature 1. in this direction feature 2, in this direction feature 3. Okay. So these boxes are all imaginary boxes. They are not physical. Okay. So from the samples, if you establish the extreme values in band 1, so from here to here to here in band 2, and here to here in band 3. Suppose you have estimated the extreme values, then you have essentially kind of a box, you can say, and if any sample values are within the bounds of any of these boxes, it will be assigned to that class. Like here, for example, this particular one belongs to class 5. It is within the bounds of class 5. Whereas here you have a sample which does not fall in any of them. So it is left unclassified. So unclassified means maybe there is a class 7 that you have not considered, or maybe class 6 or class 3 should have extended further. Okay, maybe you have not considered enough range in band 1. That's why this is not gone up to this level. This is not falling in one of these boxes. Maybe you should have more training samples to expand the size of these boxes. Okay, it indicates that you have to do more to account for the unclassified samples. Okay, so in the previous case, you are doing some calculation, Euclidean distances, okay, and then determining which is smallest, etc. Here you are doing an if-then else check. If, like here, for example, for this particular sample, if its band 1 value is within the bounds of class 5 and band 2 values are within the bounds of band 2, and if its band 3 value is within the bounds class 5, then you say that this should belong to class number 5. So this one, you can see it satisfies as far as band 1 is concerned, this sample satisfies class 5, but it fails the band 2 dimension. Okay, as well as, so once any of the checks fails, you have to move to the next class. Okay, so you can see if you have so many classes, you have so many if then else checks, and if it doesn't satisfy any one of them, it is left unclassified. So you have a slightly more robust approach that utilizes the Bayesian reasoning, that if you want to estimate probability of CI class, that is probability of class I given the data vector X, you can use the knowledge that you have already computed probability of X given CI. Okay, and with the help of prior knowledge, like what is the area occupied by each class on the ground, historically speaking. Okay, so this need not be very exact. Even if this has small errors, it's okay. But suppose from previous studies or government reports, whatever, if you know the area occupied on the ground by the forests cover, by the lakes, by the built up areas, roads, etc., if you have approximate estimates, you can make use of them to estimate this. Okay. And normally this conditional probability is assumed to be Gaussian. That is, for each class, you have a mean response, and around the mean, the reflectances fall off exponentially. So Gaussian is one of the common assumptions. And so, forget the mathematics. It's very simple if you actually look at it at your convenience. So in this equation, certain things can be pre-computed. And this is one thing that for every input data vector x, you have to compute this. And then you have to just add the extra terms, which are computed once. Okay. So G1 of x for class 1, G2 of x for class 2, etc. And finally, whichever comes out highest, the data vector is assigned to that class. Okay. So again, as you can see here, the moment I'm given the training samples, I can compute the covariance matrix for a class, the mean vector for the class. If I know the area of each class, I can use it. Determinant of the covariance matrix. So many things are pre-computed. Here, this is a constant anyway. This is pre-computed. This is pre-computed. Mean vector is pre-computed. Covariance matrix, its inverse is pre-computed. So for every new test pixel or new pixel, I have to make this substitution in this and compute this for all the classes and see which one is highest. Okay, this is the method. So I'm given the training data, I'm ready for classification. I don't have to learn anything else. Everything is fairly straightforward, pre-programmed, and I'm ready for classification. So that's why we call them programmed classifiers. This is an example. The city of Varanasi is here, and different kind of wheat and rice crops. This is actually a forest, but this is a winter image just after peak winter. So deciduous forest, all the leaves have fallen off. And so a subsequent summer image, if you see, this will be full of green vegetation. Okay. Typically, for those who are not familiar, this is how a classified image is represented. Each class is color coded and the colors are, the legend is given so that you understand what each color represents on the ground. Right. And then you have other classifiers also. What's called nearest neighbor. So instead of using the means, suppose we use the information like which is the nearest training sample of it, let it be of any class. Okay. So out of all the training samples, you suppose you find that class 1 has a training sample closest to this. So you assign this to class 1. Okay, and we have extension like k nearest neighbor, etc. We need not go into it. So far, we are given the data and we are ready for classification. There is nothing to be learned, okay, for classification purpose. But then, in all these cases, you are making some assumptions, okay, that the mean vector of a class represents the whole class, or from the training samples, if you know the extreme values in each spectral band, they are complete. They cover the entire range of values, and you can directly substitute or you can directly compare and find the class, etc. These are assumptions which rarely are satisfied. Okay, so given the data, you first learn which are the zones in the feature space relating to each class. Okay, after that you perform the classification. To learn the boundaries between the classes using the training data. Okay, so the classifier function is optimized using the training samples as constraints. That is, you design a classifier in such a way that you have the boundaries between classes in the feature space, not on the ground. In the feature space, you are able to put samples of different classes in different parts. Okay, so how do you do it? For that, you need to define an optimal classifier that should satisfy the training samples first. Before you deal with test samples and the total images, first thing is you should make sure that all the training samples are correctly classified. Then you have to go for testing, validation, and then deploy it for practical purpose. So when you say I want the boundaries between classes, okay, so can I say that the boundary can be represented by a line or a plane or a hyperplane, etc., or is it more complex than that? Some kind of a nonlinear function. So simplest assumption obviously is that if I am in a 3D space like a room, I can partition that room with, say, we have the partitions like curtains or wooden boards. So with that, you partition the room into different zones, each zone representing one class. Okay, or if it's two-dimensional like a board on which you draw a line separating each class from other class. So the boundary or the discriminant that actually discriminates between the classes is a linear function of the feature variables. Okay, so we have, for example, for a line we know y equal to mx plus c or ax plus by plus c equal to 0. We have such first order equation, okay, representing that linear feature like a line in a 2D feature space, or in ND feature space you have w1x1 plus w2x2 plus wnxn plus w0 equal to 0. Okay, so what is given here? For a two class case, I have some samples for class 1 and some samples for class 2. If I say that the boundary is represented by g of x, if a sample is on the boundary, g of x will be 0. Otherwise, g of x will be positive for some samples, let us say class 1, and g of x will be negative, less than 0 for, let's say, class 2. So my job is, given the training samples, compute the parameters of the discriminant. Okay, compute the parameters of the discriminant so that my data is classified into two classes by means of producing a positive response for one class and a negative response for the other class. Okay, so the unknowns are, for example, if you want to draw a line, what are the unknowns? The slope of the line and the intercept with the x-axis. These are your unknowns. Okay. Similarly, in a general case, the W's are your unknowns. So they have to be found. So when you are finding them, what are your constraints? Your constraints are that given training samples of class 1 should produce, let us say, a positive response, and samples of class 2 should produce a negative response. So the W's should be so computed. Okay, so we have a little maths here. You can ignore it. So there are simple optimization rules, okay, which starting with randomly assigned values for W, okay, the way they are updated. So suppose the response is positive when the sample belongs to class 2. So it means that the current values of W should be reduced. Similarly, when you get a negative response for a sample that belongs to class 1, where the response should be positive, the weights are moved up. So this way, by doing it hundreds of times, you come up with a set of W's, okay, which will then produce correct response. Given samples of class 1, they produce positive response, and given samples of class 2, they produce a negative response. So that takes care of the training phase. Okay, then you have to test it for the generalization ability, etc., etc. So this is when the data is linearly separable. Now this kind of a classifier, okay, derives from the model of the processing element in the human brain called a neuron. Okay, so the neuron is studied using its computational model called perceptron. Okay, perceptron was supposed to be able to model a single neural element in the human brain. So the model is like it receives many input responses, many inputs. Each input is scaled by some weights W. So sigma WI that gets collected in the center called a nucleus. And if this total exceeds some limit, then an output signal is generated that goes through what is called an axon. Okay, the inputs are coming through dendrites. The weights, the scale factors, they are called synapses. The center is called the nucleus. And the output is going through what's called an axon. And it becomes input to many other neurons. Okay. So the human brain contains anything like 10 billion neurons, and each neuron is connected to 10,000 to 100,000 other neurons. So that gives you a fantastic parallel network. Each neuron is a very, very simple computational element, but with so much of parallel processing, it's extremely powerful. for scene recognition, face recognition, etc., etc., for understanding music and so on. But it is very poor at numerical calculation. Okay, suppose you are asked to tell like this, how much is 19 into 17? You won't be able to tell very easily. Your parallel network is no good. Because the neurons, each neuron is very, very primitive in its capability, you require help of a calculator or a paper and pencil. So this is the mathematical representation of that, what we have seen. Inputs, multiplying factors. So they get collected in the central area called the nucleus, or here this is central area. And this quantity passes through a nonlinear function. Okay. So a threshold function is also a nonlinear function. So if net exceeds, say, some limit, then output is 1, otherwise output is 0. That is one example, and you can have other kind of nonlinear functions which are differentiable, and you can get a response which need not be 0 or 1 but fractional. So the knowledge essentially relating the inputs to the target classes lies in these weights. So you are given some inputs and the corresponding classes, and you have to determine these W's so that the inputs are correctly classified. Okay. So you understand the difference now. You don't know what the W's are. You have to determine them. So it's an optimization problem. You have to minimize the classification error. That is the difference between the computed class and the true class. The difference should be minimized, subject to the condition that is, when you determine the W's by minimizing the error at the output, you should make sure that samples of class 1 produce a positive response, samples of other class produce a negative response with this mathematical function w dot x plus b. Okay, that should produce appropriately positive or negative response for the classes. So essentially this learning is error minimization. The desired output, computed output, the difference should be minimized. So it is minimized when you hit the correct combination of the link weights. Okay, so the error itself is a function of many variables, as many variables as the number of weights. So you start with the randomly assigned weights and then move towards minimizing the error. And each time you update these weights, okay, this increment depends on what is the amount of downward step you are taking to reach the minimum. Okay, since you are minimizing a function, you are descending in the multidimensional error surface. Okay, suppose this is some kind of a profit or gain. In that case, you would have moved in the upward direction. We would call it gradient ascent. Here it is a gradient descent. Okay, so How are these W's estimated? You start randomly, find how many samples are wrongly classified. That is your error function. This needs to be minimized. How do you minimize it? What is the unknown? Unknown is the W. So you differentiate with respect to W, equate it to 0. And so that gives you the derivative. And with the help of that, you update. So this is the error differentiated with respect to the weight, unknown weight W. So this is the derivative. You want to go in the direction opposite to the gradient. Okay, because the derivative actually represents the gradient. So you go in the direction opposite. So you put a minus symbol, and this is a rate parameter, a step size parameter. Usually you change the weights very rapidly in the beginning, and then as you approach convergence, you want to take smaller steps so that you don't overshoot the minimum. So it's well known that this kind of a simple classifier can deal only with the linear separation between classes. It cannot deal with nonlinear separation. The other limitation is it gives you, even if the data is linearly separable, that is, if you can draw a line or a plane or a hyperplane separating the data, you are not given the best boundary. Okay, it gives you some boundary, but the training samples are correctly classified, no problem with it. But what happens when you have new test samples? The perceptron does not care about it. So a better classifier, which is an extension of this simple perceptron, is the support vector machine. So what does the support vector machine do? It tries to give you the best classifier. How does it do? So suppose you are given the samples of class 1 and say class 2. So you can draw boundaries, any one of them. All of them have class 1 on one side, class 2 on the other side. All of them give you 100% accuracy as far as these samples are concerned. But what happens when you have new samples, test samples, test data? These are all training data, fine. What happens when you give test data? Suppose this is the boundary. You see the samples of class 2 are very close to the boundary. So if you have a test sample whose value of this particular feature is slightly more, it goes into the wrong class. Similarly, this one, if the value of this particular feature is slightly less, it goes into the wrong class. So you have very small margin for the test samples to vary near the class boundary. Okay. Whereas if you use this one, for example, relative to this, you have much more margin. So samples of this class can go all the way up to the boundary. So you have much more margin available. Okay. So this particular classifier is designed in such a way that you find the class boundary in such a way that you get the highest margin for the test samples. So what is this margin? when I'm using the term margin, what am I referring to? The margin is the distance between the class boundary and the nearest samples. So these are the nearest samples. This is the nearest sample here. Okay. So the nearest samples belonging to the opposite classes, okay, how far are they from the boundary? More the distance of the nearest samples from the boundary, that much more margin I get. This is the principle of support vector machine. The mathematical function of this class boundary is determined by the nearest samples, which are, mathematically speaking, the support for this function. All the faraway ones are irrelevant. You don't care about them. For you, the most important ones are the nearest samples. Draw the boundary in such a way that you get a maximum distance from the nearest training samples. Okay. So supports, these are the nearest training samples that are supports. Generally, we have the data in multidimensional space, so we call them vectors anyway. Support vectors. The machine is a classifier. Support vector machine is a classifier. Okay. So mathematically speaking, we need to find the parameters of this thing. So you have to find, for every discriminant, you have some margin, okay, given by the samples which are at minimum distance from this. And you have to find that boundary which maximizes this margin. Okay. So what your task is to search for that class boundary for which the margin is maximized. And what is the condition, constraint? Constraint is that all these samples should be on one side, all these samples should be on the other side. They are the constraints for you. Okay, essentially this is the principle of a simple linear support vector machine. Okay, so what you need in order to identify the support vectors, you have to find the distance of all these samples from the boundary and then find those which are at minimum distance. Okay. So if you are given the discriminant boundary, you can find the distance of every sample X and then find the minimum. So which are the X for which the distance is minimum? There is the first step. The second step is find the W and B for which the nearest distance is maximized. Nearest distance is your margin. Okay. So you want to maximize this. Okay. So for every W and B, you find the support vectors. So for which you will get the margin. So find those W and B for which the margin is maximized. That is your support vector machine optimization problem with the constraints that the samples of class 1 produce a positive response, samples of class 2 produce a negative response. Okay. So if you assume that the margin can be normalized to 1, so the numerator can be reduced to 1, and so you have 1 by this quantity to be maximized, or this quantity the denominator should be minimized. Okay. These are the algebra for you. Don't worry about it right now. Support vector machine is explained in almost all machine learning textbooks, and tutorials are there plenty. So here I skipped two issues. That is, what do you do when you have noisy data, outliers? Okay. In case of outliers, what you do is you assume that the classification accuracy is not 100%. Some samples are bound to be misclassified. Accepting that, you try to maximize the margin. Okay. That is, suppose a black circle, that is, this sample is on this side due to noisy measurement, sensor malfunction. Similarly, this is on this side. You cannot do anything about it. You cannot draw a boundary where all samples are on the correct sides. Impossible. Okay. So in that case, we provide what is called a slack parameter. The slack parameter tells you how much error can be accommodated. And the second is, what do you do when the data is not linearly separable? Okay, so you need a parabolic or a circular or some other kind of function. Okay. So how do you deal with such situations? Okay, for which the pre-processing step is all the data are nonlinear, passed through a nonlinear function. Okay. So by passing it through a nonlinear function, mathematically speaking, the data is transformed to a higher dimensional feature space. So the probability of the data being linearly separable increases through this nonlinear transformation. Okay, there is a set of mathematics called Cover's theorem, etc., which are the basis for such steps. So whenever you're using support vector machine, you have to supply the training samples. You have to also supply the slack parameter value and which nonlinear transformation function you want to use. Okay. And then you have a trained support vector machine, and then you can provide your input image for classification. So SVM is one of the very, very popular classifiers today. One of the best machine learning algorithms for remote sensing applications. One of the reasons is in remote sensing, sometimes you may not get sufficient number of these training samples, particularly with the hyperspectral sensor data. It is not easy to get enough training samples. As you can see, an SVM just requires as many samples as the support vectors. You don't need all the faraway samples. Neural networks require all, whereas support vector machine requires only those few which represent your support vectors. So if you have small training data sets, SVM is the tool to go for. You have classification example with remote sensing. So the input data is here and the classification result is here. I've given you the reference so you can look up the original paper if you like. Now, what do you do if you have a perceptron, but the data is not linearly separable? So then in that case, what you do is you stack up these neurons or perceptrons in layers, stages. So here you have a partial classification with this step, some more partial classification and final classification when you come to the output stage. So between the inputs and the outputs, you have what are called hidden stage. What you have a hidden stage comprising a set of perceptron elements, okay, which are hidden from the end user, but not from the programmer. But so for whatever reason, they are called hidden layers. So the process is you have partial classification from here to here, here to here, and here to here, so that even if the data is not linearly separable, you can still deal with it with a multi-stage or multi-layered network. So you have to supply information inputs like how many elements in the input. So how many features are there? That is your input. How many classes are there? That is the output. And in between you have one layer, two layers, or more layers in the hidden stage. And in each layer, how many elements? These are, you can use either the defaults in your program or you supply them. You feed the input, these numbers yourself, if you are familiar with the neural nets and your data. Generally, the algorithm is feed the inputs left to right. When you reach the output stage, find the classification error, feed it back to correct the weights till such time you get proper classification. So since the error is moved back, error is propagated back, the training rule is called error back propagation rule. So again, the same rule, move along the negative of the gradient. Only risk is sometimes you may reach a minimum which is not the global minimum. So the gradient becomes zero here and the weights don't change anymore. Whereas you would have wanted the this set of weights where the error is much less. Okay. So you have to first verify how low is the error and then maybe change the input or the weight starting. There are a lot of tricks involved in with the neural networks to come to a satisfactorily low error. I'm only giving you an overview. Typically with neural nets, you have problems like it's not learning enough because there aren't enough hidden layers, or it's not able to generalize. Either it doesn't have enough training data or it has too many hidden layers. So for the size of the network, you don't have enough samples, so generalization is poor. So typically you have, for example, image like this. So what inputs do you give? Size of the input layer, how many spectral bands? Size of the output layer, how many classes? How many hidden layers, etc. And you get nice classification like this. If you don't have enough features, you can then derive more features from the data itself and then carry out the classification. So in this example, I've used texture features. I added them to the input image and then used a neural network for classification. Okay, Professor Mushrif, how much time do I have? Is it time to stop or can I take a few more minutes?
Sir, you can take few more minutes. No issue.
Thank you. Thank you.
Yeah.
I'll just give a hint of what is today's popular thing like deep learning with convolutional neural nets. Okay. So far, what we used, we can call it traditional or standard machine learning. So this is relatively more recent. Okay. So in case of traditional machine learning, the user decides what features are to be used. Okay. And what classifier to use. Everything user decides. But it may so happen that we don't know which are all the useful features. Okay. So sometimes our machine learning exercises will be limited to the data we are working with. But if we are given a new set of data, like for example, if I'm using Mumbai data, now if I'm given Chennai data for testing, will the classifier trained with Mumbai data, will it work satisfactorily with Chennai? Both are coastal cities, or Visakhapatnam, or some place in Orissa. So will they work? So the more recent research is to fully automate it and make the model as general as possible so that it should work with any new data. Okay, that is the hope with which many of these models are being evolved. Okay, so I'll talk about a very general convolutional neural net. Okay, not any specific net. There are so many of them in use. Okay, today, of course, the deep learning has come to such a level that you can create fake videos, you can create fake audios. That is simply generate images, videos, or audios mimicking any person. That is so much of understanding modeling. That is so much such powerful models have come up. Not only that, suppose somebody is giving a lecture in English in India, its Spanish version can be shown live in Spain using your own, uh, like holographic 3D image. So when you speak, it looks as if you are speaking in Spanish. In Japan, you'll be speaking in Japan. Okay, in China, you'll be speaking in Chinese, all at the same time. All you're doing is you're speaking in English in India, but in all these countries, people will see you speaking their local language. So that is instantaneous, uh, recognition, speech recognition, instantaneous, translation. Everything is happening today thanks to both supercomputing and the uh, high performance communication networks like 5G, even 4G, not why only 5G, 4G also. Okay, so a convolutional neural net, it is based on the assumption that particularly when you are using images, the information is highly localized. That is, you have pixels which are related to the neighboring pixels and not to faraway pixels. Okay, So given the size of this local neighborhood, okay, whether you want to find the boundaries, whether you want to find similar regions within the image, whatever, so you can use the local neighborhood based operations using convolutions. Okay, so you have very few pixels which will be neighbors of for any pixel, so the size of the neighborhood will be much smaller, whereas in the traditional neural networks that we have seen, every element of a layer is connected to each and every element of the subsequent layer, so the number of connections are huge. Okay, whereas here the number of connections are much less. At the same time, you can generate as many features as you want with several stages of these convolutional filters. Okay, so through these convolutions, you generate the feature vectors, and those feature vectors are classified. So your training rule learns the relation between the feature vector and the class, as well as the coefficients of these filters. Okay, for those who are particularly from non-electrical engineering, of course, it's organized by electronics and communication, so I'm assuming everybody knows what is convolution. It's a weighted summation of the filter coefficients with image pixels. Let's skip through this quickly. So you generate such filtered images. As many filters you have, that many images you generate. Ultimately, you get what's called a feature map. Okay, so there are various steps involved, like you generate some convolution outputs, then you combine them through what's called a pooling stage. Then you apply one more set of convolutional filters. Again, do the combination with pooling. So like that, and then you generate the final feature vector. Okay, that is supposed to belong to some class. Okay, so for each class, you generate these feature vectors. So that is the training phase. Now the entire image data can be classified. So for each pixel block, you generate the feature vector, and that block is assigned to some class based on the trained convolutional neural network. Okay, so the convolution stage is used essentially to generate the feature vector. And the training in case of CNNs typically happens with the help of small, it's not with individual pixels, but small image regions. Okay, so the region can be as small as 32 by 32, or it can be bigger, or it can be slightly smaller, whatever, but depending on this image window and the number of convolution stages and the in between combination or pooling stages, you have these final feature vectors. Okay. So the pooling step is introduced with convolutional neural nets so that you can make the data more homogeneous by combining whatever values are generated through the convolution stage. You can make it more homogeneous by usually you have uh, say with small blocks you take the maximum or minimum or average. Okay, so this information you can get from any of the CNN uh, tutorials. Okay, since we are coming to the close of this lecture, can't give too many details. You have various.
Sir,
Yeah.
sir, I have one question.
Yeah.
Like in pooling, we can either use max pooling or average pooling, and then we go for downsampling. So, will there will be a loss of information, and how we are going to cope up with that?
See, so the pooling is essentially to reduce the dimensionality. So it is assumed that since the feature vectors you generate are so large, the pooling does not cause much problem. Pooling, even if you avoid pooling, you can still go ahead with generating the feature vector and do the classification. Pooling is only an optional step, but it is used essentially for reducing the size of the final flattened feature vector. There is another classifier called capsule network where it doesn't use the pooling. Okay. Now, the CNN was like Professor Hinton is one of the main contributors to this CNN. He himself has, denounced this pooling step, and he developed a new classifier called the capsule net, which does not have this pooling stage. Okay, but
Okay.
the training rule, with the training phase, etc., is much more complicated.
Mm-hmm.
But more recent developments in capsule nets, I think, overcame the problem. But it is relatively, more complex to train a capsule net. But you have, again, in remote sensing itself, you have many papers today of capsule net based classification.
Okay. So, pooling won't affect that means. So it's
Yeah,
optional.
pooling idea is essentially to
Reduce the size.
reduce the size,
Okay. Thank you, sir.
because let us say 2 by 2 is reduced to 1 na? So
Mm. Yes.
you're getting 1/4 the size.
Yes, sir.
So a quick very quick introduction to this high dimensional data called hyperspectral data. So today, if you are a field scientist, you go for what is called a matching approach. So from the field studies, you have a set of reference signatures or libraries. And for every pixel, you have the feature vector, and you do a matching and identify. Typically, this is used to say, are there traces of copper in the soil, or are there traces of say uranium, etc. So in such studies, the full spectra are used, and along with a set of libraries, and so the spectral matching is used for target classification. In the other side, purely image processing wise, when you go, first you perform a dimensionality reduction because you have a very large number of spectral bands, dimensionality reduction, and then you get your training data and then perform your classification, etc. So there is so much here that is there in hyperspectral images.
Uh,
One of the, yeah,
Sir, I have one question here. As only atmospheric correction is mentioned in case of high spectral resolution images, what about other corrections? They don't need like geometric or radiometric?
see, you don't normally do the geometric correction in the beginning because geometric correction involves, mixing pixel spectra
Hmm.
through interpolation, etc. So unless you have a mapping requirement, you generally don't do the geometric correction in the beginning.
Okay.
Yeah.
And what
So what
about
you can do
radiometric?
is, yeah, radiometric in the sense if you have sensor errors, yes, you have to apply suitable corrections for sensor noise.
Hmm.
Um, uh, but if you have, uh, you know, at, normally you have the atmosphere as the main villain of the story
Yeah,
here.
yeah. It is
So
two times
atmospheric,
it is
mm,
getting interacted with the matter.
yeah. So atmospheric correction is more critical,
Okay.
and for example, average kind of sensors, you have very stable sensors, whereas the first satellite-based hyperspectral sensor, it had a lot of sensor problems also, like
Hmm.
Hyperion, the NASA's hyperspectral sensor had a lot of sensor problems as well. There you needed radiometric correction also.
Hmm. Okay, okay, okay. And as you said that it is in hyperspectral case, the mixing is there, right?
Yeah,
Unmixing of frequency is needed over there. So could you highlight on what exactly
yeah,
that
yeah,
mixing
yeah.
unmixing model is?
See, there are two things. One is because the sensor elements operate in very, very narrow wavelength bands,
Hmm.
and since it is impossible to get perfect, uh, you know,
Spectral
uh,
signature separation.
spectral, perfect, that is one element to the next element,
Hmm.
there will be some overlap.
Yeah.
Okay. Suppose you say 10 nanometers to 20 nanometers is one sensor bandwidth, and 20 to 30 is the next one.
Hmm.
So the first one will not have exactly 10 to 20. It may start at 5 and it may go up to 25. But the best highest signal response will be in the 10 to 20 range, but to the left of 10 and to the right of 20 there will be some uh, you know like signal collected in those adjacent bands also, so there will be
Hmm.
overlap in
Hmm.
the spectral response of adjacent band, so that correction is different. uh, so for that, usually the people who collect those data, they carry out such corrections.
Hmm.
As for the end user, it is typically the mixture modeling.
Hmm.
Atmospheric correction, if you are planning to collect the data, that is the ground truth data and the atmosphere data on the
Hmm.
date on which the image is collected,
Oh,
you can perform reliable atmospheric correction.
okay.
If it is some old data, today you can't do much except making some as general assumptions like which part of the globe on
Hmm.
which where the image is collected, and what is the season, what kind of area is it, urban or rural.
Hmm.
Okay,
Hmm. Hmm. Hmm.
so is it coastal or interior away from the coastline.
Hmm.
So there are a lot of assumptions on which general corrections are made, which improve the data but may not be perfect. If you have synchronous uh, this ground truth collection and atmosphere data collection, if you're able to do it, then you'll get the best atmospheric correction.
Okay. Thank you, sir. Sir, and it means if we are talking about atmospheric correction is the first step, and then we can go for other spatial enhancement if needed with respect to the
Yeah.
classifier. So
Atmospheric
two
correction is the
two
first step.
steps of corrections would be the pre-processing step.
Yeah.
Okay. Thank you, sir.
So usually, when you have very high spectral dimension, what happens is whatever energy is coming from the ground is divided into a lot of slices and fed to different detectors. So the amount of energy available to each detector will be very little, right? Because the sensor requires sufficient amount of energy for reliable, generation of a signal that is above the background noise level. What is normally done is the pixel footprint on the ground is made bigger so that you get more energy, and so when you divide it into different spectral bands and feed it to different detectors, each detector receives sufficient amount of energy. This is particularly true for satellite based images.
Yes.
So each pixel, if it occupies a large area on the ground, then in that area you can have multiple classes, right? So for example, the first space-based hyperspectral data, each pixel was 900 square meters, 30 by 30. So imagine, unless you are in Himalaya, say snow-covered areas, deserts, oceans, or large Amazon-like forests, etc., 900 square meters, you rarely have a single class, right? So you have a lot of
Right.
mixing.
Yeah.
You have mixing.
Yes.
So unmixing has to be carried out, and then only you will get proper classification result.
Yes.
Okay?
Yes, sir. Thank you.
Yeah. Now, so the estimating the proportion of a class inside a pixel is called abundance mapping. Okay, so there are linear programming models for linear mixing. That is W1 times class 1 plus W2 times class 2, etc., make up the total reflectance at a pixel. So W1, W2, etc., they have to be
Yeah.
estimated
So
subject to the
corresponding
constraint that,
coefficients we need to calculate for that
yeah.
class.
So that constraint is W1 plus W2, etc. They should add up to 1.
Yeah.
So if you find the relative proportion inside a pixel, the next step is where are these subclasses within the pixel? That is called subpixel classification. Okay. Suppose a pixel contains 30% water, 70% vegetation. So where is this 30% of water in the pixel? Where is the 70% vegetation? So that is the subpixel level classification. Okay, now if I have the subpixel level classification, and since I know the true response of each class, can I generate an image at a higher spatial resolution? Okay. So I know that pixel contains 4 classes, and I know where those 4 classes are inside the pixel, and I know the response of each class, spectral response of each class. So I can then simulate a higher resolution version of the image, okay, where there are no mixed pixels. That is called super resolution problem.
Okay.
Okay, so these are the research areas with hyperspectral data. So I'll wind up now because we have crossed 9 o'clock. There are examples for you You can even search for papers with my name as one of the authors. You'll find examples for pixel classification, super resolution, etc.
Okay, sir.
Yeah. If you want with high resolution, high spatial resolution data, you have now object detection where you define the object, and so each object is enclosed in a region. So this is more region-based classification, and so this is, you train it for aircraft and you detect all the instances of the aircraft, or you train it for building and you detect all the buildings, like that. It was. We have similar workflow for high spatial resolution images also. You first break it down into regions, then generate features for each region, and then you can do object specific classification or general purpose classification. So like this is for buildings, this is for coastline, this is for roads. So there is, I mean, we run this course for 2 semesters. Whatever I tried to cover in 2 hours.
Sir, I
Thank
have one question.
Please.
Sir, in a matching,
Huh.
you are using their library, spectral library. Okay.
Correct.
So,
Yes.
so that library will be fixed because as the time is goes on, means after 10 years, the structure of some area will be changed. Or so
Yeah.
in that
So
case, what we will do?
So the spectral libraries will have to be updated.
Update it. Okay. That will be not be fixed, no?
Yeah, in the sense, uh, suppose you say that you are looking for mineral X.
Hmm.
Mineral X response will not change.
Okay.
Okay.
Hmm.
So, but if you have some, say,
Vegetation, forest, or
compound, some compounds of that spectra, compounds of that element.
okay.
Suppose you are able to find not just a pure element but different so today you found some compound of that, and
Okay.
maybe tomorrow you found another compound. In that case, you
Okay.
update the reference libraries.
Okay.
Okay, so updating the libraries will happen with time,
Okay.
but some things will remain fixed. Okay.
Okay. Yeah.
Yeah.
Okay. Thank you, sir.
Right.
Sir,
Yeah,
Uh,
please.
yeah. In hyperspectral image classification,
Mm-hmm.
one of the blocks was dimensionality reduction. So,
Correct.
can you elaborate the techniques used for dimensionality
Yeah,
reduction?
dimensionality reduction is, in a sense, the search for a set of useful features within the total number of features given by the sensor.
Okay.
Okay,
So,
so that
redundant
is,
features are removed.
yeah. So you try to discard the redundant features and select the most useful ones. So there are actually two methods here. One is called feature selection, that is within the given features you select the best subset.
Mhm.
Okay, so you use search methods like genetic algorithms, ant colonies, etc.
Okay.
Okay, that is one approach. The second approach is feature extraction. So you transform the data like principal component transformation or
Right.
independent component
Independent component.
transformation, etc.
Mhm.
And after the transformation, you now select the most useful transformed components. There you can have some kind of a criterion,
Mhm.
okay, on the basis of which you can discard some components and you select the rest.
Okay.
So feature extraction versus feature selection. So these are
Mhm.
the two approaches for dimensionality reduction.
Okay. Any other questions from the participants?
Maybe they are hungry now.
Okay, sir.
No,
Not
most of the
surprised.
questions have been asked in that detailing.
Right.
So, sir, your session was information-packed session. You covered almost everything. Like you said that means you have packed 2 semester course into a 2 hour.
Yeah, I just gave you glimpses of two
Yes,
semester
yes,
course. I myself teach at IIT.
yeah, yeah. So those who are means more interested can explore it further.
Yeah.
So you started with the definition of what is remote sensing, and then uh, then you discussed about the sensors, specifications of sensors. Then you also discussed about the conventional classifiers like minimum distance, maximum likelihood classifier, and then learning based classifiers. And then you discussed about neural networks, multi-layer perceptrons, and then you also touched about upon the deep learning algorithms, hyperspectral image classifications, and so on. So you covered almost every aspect of supervised classification here. So it was a very nice talk. Uh, we could learn so many things. Some of the things were known to us, but that was a revision, and we learned many more things from your lecture. So, thank you very much, sir, for accepting our invitation and for giving such a nice talk.
Thank you
And
very much for
yeah,
inviting me, and
yeah,
I'll email the PDF version of
yes,
it to you.
yes, sir, yes,
You
sir.
can share it with the
And
participants.
in future, we would like to be in touch with you.
Sure, sure.
Yeah, yeah.
Actually, I came to Nagpur in December.
Mm.
Maybe next time when I come to Nagpur, I'll try
Yes, sir.
to
Sure,
visit your
sure,
college.
sure, 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 sir. In our college, we have a group of some 5 to 6 faculty members who are working in the area of image processing. Some of them
Excellent.
are now working in remote sensing, and they are having good connection with MRSAC
Very good. Very
and
good. Yeah, yeah.
NRSC also. And some
Yeah, I
of
was
our
actually at
students,
MRSAC for a meeting.
yeah, and few students are also there doing their internship at MRSAC at present,
Okay. Yeah.
and they are attending this workshop also. So it was very nice to mm, see you here. Thank you, sir, very much.
Thank you
Yes.
very much, and
Yeah,
all the best for
yeah,
the remaining part of the course.
yeah.
And I'll email you this presentation.
Yes,
Yes, sir.
yes.
Yes, sir.
Thank you. Thank
Thank
you
you,
so
sir.
much, sir. We also run a semester-long course in digital image analysis for remote sensing along with MRSEC, sir, at our department.
Okay.
Yeah. Dear participants, I would request you to please switch on the video for a group photo. Sir, we will have one group photo and then
Sure,
you may
sure, sure.
discuss. Hello, participants, please switch on the video for group photo.
इथं मला नाही काही करू द्या लेआउट.
Okay, wait. Let me stop the screen sharing.
Okay.
Okay, now.
Very few have turned on the video. Please turn on the video for a group photo. I will take one more. Thank you, sir. It's
Thank
done.
you very much. Good night and all the best.
Yeah.
Yes.
Good night, sir.
Good night, sir.
Yeah.
Dear participant, tomorrow again at 6:45 we will meet for another sessions from day 5, and I have shared the attendance link in the chat box, so please fill the attendance before leaving the meet.
Madam, once again send, please.
Yeah, sharing. Is it visible? Yeah.